some of them, like, I think it was the one after 7, like 15 or something, where it only accepted 3 A's. And like get into a trap state with the B.
Yeah.
Or it accepted any amount of A's except 3 A's. Did we have to have an edge going out of every single one of those to a trap state for
Say
B?
what you meant to be accepted.
Did it say what the language
I just knew there was
associated?
I was like, okay, let's add them somewhere.
Or the alphabet was. It didn't say what the alphabet was. I am fine then, if assuming it's alphabet of
What was
A's.
the goal for this one? What you meant?
If you said it's an alphabet of A's and B's, that's also.
I think it's.
If the problem didn't specify, I can't mark you down for information that's not there. As long as your solution is correct for whatever it is that you assume.
If you told us what we were meant to be accepting, it'd be like 1,000.
Specify.
Yeah, that's perfectly fine. If the information wasn't there that said there's more than that, then the answer is perfectly correct, given the information that you had.
There's more than that, then I have to consider it.
Exactly.
I'm just asking what this one was.
Exactly.
Okay, because this one, if you have a PDF, it doesn't go anywhere, so it's, that's where the trap is supposed to be.
All right, tomorrow you're getting a study guide. There's an assignment up. We talked about 2 different deadlines. There's a Monday deadline and a Wednesday deadline. The Monday deadline is if you want feedback on assignment 2 ahead of exam 1. And the Wednesday deadline was you will get credit, but there is no guarantee. We'll still do our best to get you feedback before the exam, but that gives us 1 day to do it. And depending on the number of people who submit on Monday, if almost all of you submit on Monday, then maybe the few people who submit on Wednesday will also get turnaround, because then we'll have Tuesday and Wednesday to get you feedback for most of the class that submits on Monday. That said, if 2 people submit on Monday and everyone else submits on Wednesday, then we have almost 30 assignments to grade in 1 day. And that's for something that's as complicated as this class, that is not going to happen.
Did you included both chapters on the study guide?
Yeah, actually I can do that.
Or should we just assume that they're just the only chapters
It's
or chapter sections from the homeworks? Because like I don't want the homework started.
I don't put anything on there that is from the book, but not from class. Everything that is an exam question will have been covered in class, but I can certainly give you the reference material for all of that. I still need to give you the week 2 chapters that you asked for yesterday. That's still on my to-do list, and I think I can get to that today because I'm not teaching for 2.5 hours in the afternoon and then having everything else I need to do in an evening. So I think I can get to that today. I think that's everything you need to be thinking about. Anyone else think of anything that I'm not thinking about? Assignment, study guide. We have a review period on next Thursday, a week from today, and an exam a week from tomorrow. I know it's a very quick exam, but given the pace that we're going, it's much better to have more exams than to have a single exam that covers twice as much material as we've already covered. That is a lot to put you through, so that's why I have 4 exams in the class. It's a lot less material to know, and it also means that you can put as much as you want on that sheet of notes front and back. We don't want to cram that to the point where something gets cut from it because there's just too much information to put on it. Also, larger sample sizes are better than smaller sample sizes in general. Questions before we dive into the last slide of regular expressions and then starting to talk about regular grammars? Right. So we got through a practice problem on the regular expressions yesterday, just thinking about the different ways and the equivalences of coming up with different regular expressions for this particular language. We also saw some of the different reasoning and logic that led us to each of those solutions. So I'm hoping that somewhere in there is something that you can latch onto as yeah, that makes sense to me. That's the way that I like to think about generating regular expressions. If not, I'd be happy to meet with you in office hours and hear your thinking and work with you to come up with an intuitive way for you to generate solutions to these kinds of problems. We ended the class talking about that 2 regular expressions are equivalent if they represent or denote the same language. So here are the 2 different answers denoted the same language. So these regular expressions are equivalent to each other. One of them is shorter. I'll leave it up to you to say which one is more intuitive, because we will differ on which one of those is more intuitive as far as their internal construction. Tying this just to everything we've talked about with regards to regular languages, we said that there can be many regular expressions that represent the same language, but each regular expression itself represents one and only one regular language. So language can have multiple expressions that represent it. An expression can denote one and only one language. This is exactly the same as we found for DFAs and NFAs with regards to regular languages as well. There were multiple different DFAs that represented the same language, but given that we had a DFA, it was a DFA that recognized one and only one language. So it's exactly what I just said. So kind of the back and forth. There's a many to one and one to many relationship between language and regular expression. If we wanted to actually go through and prove this, we could construct an NFA or a DFA, accepting the language represented by a regular expression, doesn't matter because we showed their equivalence. For part two, for every regular language, there exists one or more regular expressions. All you have to do is generate an expression that does that. You can generate the labels from all of the possible simple paths that exist in that NFA, and you can use that to construct a single regular expression, and then you can use that to show, given an arbitrary NFA, we can now construct a regular expression from that NFA. I will not go into that in incredible amounts of detail, nor do I expect you to know how to do it. That said, it's important to know that that is how you would show that. We'll get into this a little bit when we talk about the pumping lemma. We'll see if we get there today. Regular grammars are a little bit quick. If not, we'll start talking about that tomorrow. But if we have cycles that can be traversed arbitrarily or in any order, then that creates a bit of a difficulty, and that's the hardest part of proving this part two. There's this concept of generalized transition graphs that we can use to make this easier. I already know, given my history with this course, I don't really have a ton of time to come back to the as time permits ideas because there's just so much to cover that but who knows, maybe this quarter will be different. If there are times that we can come back and cover something that I glossed over in terms of this is complicated and cool, but we don't have time, this could be one of those ideas to come back to. How do we actually prove this concept? Probably not the most engaging or exciting topic to come back to, but it is an option. Questions on anything from regular expressions? It's the end of what I'm planning to cover over them. For now, at least. Right. Into regular grammars we go. All right, so we know about grammars. We've talked about grammars a little bit. We've done some homework problems on grammars. However, the grammars that we looked at were not necessarily regular grammars. So what restrictions do we need to make to the concept of a production to be able to represent regular languages and only regular languages? So refresher on grammar concepts, we had terminals. Those are characters within the alphabet. Non-terminals were these concepts of variables that represented abstract ideas or more complicated structures that would break down into additional non-terminals and possibly some terminals. This gets defined and eventually broken down to the point where any one of these non-terminals could be broken down into strings that represent sentences in the language written that this grammar represents. So terminals are kind of like primitive variables and non-terminals are kind of like objects. If you looked at the fields of an object, the fields of an object are either other objects or they are primitives. And if they are other objects, those objects fields would break down into possibly some other objects, but also some primitives. And eventually you could break down any object via looking at its components into nothing but primitives. So objects are just ways to group primitives together in ways that have some kind of meaning. It's saying these primitive fields together represent some larger scale object. So you can think of grammar terminals and non-terminals in that way. And I think that helps to make it a bit more intuitive, especially given your CS course history. Questions on that analogy? Does that help to understand kind of what a terminal and non-terminal are? All right, let's talk about these exact restrictions. So we're going to call this either right linear or left linear. So a regular grammar is one or the other of those. If we have a right linear grammar, we can have two different kinds of productions. One, A arrow XB, where X is any string of terminals, and B is a single non-terminal. Or A arrow X, where X is some sequence of terminals. B is a single non-terminal. So if there is a non-terminal in a production, there will only ever be one, and it will be at the furthest right position. However, we allow for an arbitrary number of terminals preceding that single non-terminal. As you might expect, left linear is exactly the opposite. Now the non-terminal comes first. And after that come any sequence of terminals. Question?
Would this be compared to like reading left or right on a page?
Yep. And it's the exact same of a DFA. You could start at the start state and work forward to a final state, or you could reverse the idea, start at the end of the string, start at any of the final states, and if there exists a final state that you could start at and work your way backwards to the start state, then you would accept it. But then you'd have to do that for every single final state. So it's much easier to start at the one start state and move forward, looking to end at one of many final states, than look at starting at any final state. And if there exists one or more, then you could work your way backwards to the start state, then you accept. That's a lot more work, but it's comparable to this idea. Yeah.
So you can't recursively produce yourself, like A derives XA again?
That would be okay.
It will be okay?
Yeah, B can be any non-terminal.
Oh, okay.
Yeah, so you can self-reference.
Okay.
We just need to be able to linearly be able to produce the string from the grammar. There's no recursing in the middle. We're only recursing only ever at the beginning or only ever at the end. Let's give you an example. Any questions before we dive into examples? All right, here are our productions. First of all, left linear or right linear? Left linear. All non-terminals start first or come first. This is okay. All of these productions are valid productions for a left linear grammar. We could do something like this. Say, starting with the start non-terminal, we're going to apply that one production, allowing for capital A, A, B. Now we need to define that capital A. That capital A will become capital A, A, B. Then that capital A becomes a capital B. And then that capital B becomes a single A. And we have a sentence in this language. Questions on this example or this derivation? Let's see another one. Left linear or right linear?
You
It's mixed. Is that allowed?
Mhm.
No. This is not a regular grammar. So the entire grammar must adhere to left linear rules or right linear rules. You cannot mix them. So it's pretty straightforward given what we already know about grammars. The limitations are pretty straightforward. You either have a left linear grammar where the non-terminals in every production come first, or a right linear grammar where all the non-terminals come last in their associated productions. So I say all the non-terminals, meaning the single non-terminal for each production from an arbitrary number of productions. So the next thing we might want to try to figure out is, okay, if this is the definition of a regular grammar, then how could we show that this is complete? Could we take a regular grammar and construct some DFA or NFA out of it? Could we construct a grammar out of a DFA or an NFA? How do these concepts relate to each other? So we're going to start assuming that we have right linear example grammars because they are a little bit easier to work with in this case. So we have something like we're going to call it capital V sub 0, meaning variable, I guess. So we can now have V sub 0 arrow A, V sub 1, V sub 1 arrow A, B, V sub 0, or B. And the reason we use this notation here is we're trying to connect this concept of non-terminals to this concept of states. What happens when we are trying to convert this grammar into a state machine? Whenever we have that non-terminal represents a state. So states representing each non-terminal. So now we can make states V sub 0, V sub 1, up to V sub f. We know that V sub f is going to be a final state for whenever we get to a point where we would be able to terminate this grammar. That's not going to be considered as a non-terminal because a non-terminal still breaks down into some number of components. Once we read the V sub 1 arrow B, on a B, we've gone from this internal node V sub 1 to be able to produce now a sentence in that language. But we had to make that transition and add that B in the place of V sub 1 to be able to do that. Does that make sense? Sometimes I have no idea how much what I say makes sense or not. Yeah, let's dive into an example. Yeah.
When you're creating the DFA for this, you'd have to have, like, if for V1, your arrow to the A would it be A, AB?
Yeah, so you'd have to have another internal state representing the halfway point between the A and the B. Because you can only consume a single character in a DFA, but it would be equivalent of if you could have an edge that consumed multiple characters, that you would be allowed to do that. And oftentimes that becomes the draft of what you start with. On an AB, we go from here to here. Well, we can't do A and then B, so we're going to split it into A, another state, and then B.
Okay, so you would have to have like states between your next state equal to the amount of terminals.
Yeah, let's actually start drawing this out, because I think it'll make a lot more sense if we start drawing it out. So we have V sub 0 representing the starting point in the grammar. So the start non-terminal in the grammar is equivalent to the start state. So what can we do to get to V sub 1? It says V sub 0 can reach V sub 1 as long as we consume an A. So this is the equivalent of on an A, we're going to transition to a state that we're going to call V sub 1. You consume that A, and then the rest of this string is going to be whatever path we take from V sub 1 to termination. So V sub 1 can, on a B, immediately terminate and accept. So we need to be able to, on a B, move to what we're going to call B sub F, which is final. Because we have a way to terminate from the grammar, because AB is in this language, right? If we were drawing out this B sub 0, arrow, A, B sub 1, arrow, and now we need to make this and turn that into a B. AB should be in the language. If we look at a DFA here, B sub 0 on an A goes to B sub 1, on a B goes to a final state. This says that AB is also in the language. So B sub 1 says that on an A and then a B, we get back to B sub 0. So we're going to add an A to a state that we haven't been. It's a partial somewhat state. So I'm going to leave it up to us what we want to call this state. It doesn't represent one of the non-terminals in the grammar, but it represents a partial midway point. So I don't know.
1A.
Middle point 0, doesn't matter. Doesn't matter at all what this is called. And then on a B, we would transition back to B sub 0. And now we have a state machine representation of this grammar. We've mapped every production to a sequence of transitions from states. Some of those states are going to represent non-terminals. Some of them are going to represent middle points as you are transitioning from one non-terminal to another non-terminal. Questions on that? So I guess always start with that process. States for every non-terminal, including an extra final state. And then just start from the start non-terminal and start applying those productions as transitions. And just iteratively build out the grammar from there. Just everything we've already said. And it gives us exactly what I just drew. Note that the result of this is an NFA, because we didn't go through and say, we should turn this into a DFA. It would be very easy to do so. None of this is going to involve lambda transitions, although it could if we had something like if we go straight from a non-terminal to a non-terminal, that represents a lambda transition. Although, one thing to note is that imagine we had this grammar. I'm gonna make it as absolutely as simple as possible. Can we simplify this grammar?
Yeah.
Yes. We could just say B sub 0 arrow A. It's the only sentence in this language. But whenever you have this, you can just back propagate and say any definition for this can just become a definition for this. Because this is kind of a useless production. It's like saying I'm going to make an object and the only field in that object is another object. With no further methods that distinguish these objects. What is the point of that second object? It should just be an instantiation of the first object. There's no difference between the definitions of those objects. All right. So regular grammars from, I guess, regular expressions. Let's give you an example regular expression. Here is a language, AAB star A. Can we derive a right linear grammar from this? I'm just going to pause here for a second and let you think about this and work through it. Given this language, how could you produce a, let's say, right linear grammar from this? What would that process look like? Start with just a first production. What do we know about the state of any string in this language? Any sentence that's in this language? Starts with AA. So that allows us to do something like, say, S arrow AA something. B star says that there could be an arbitrary number of Bs. Is that something that we can specify with terminals right here? We need a non-terminal representing there are 0 or more Bs here. So let's just say, let's just make a non-terminal for that. And say every string starts with AA, but after that, we need some additional logic to be able to represent some arbitrary amounts of repetition. We're gonna call it recursion because I think that's easier to link to than looping.
Always end with the single A.
So defining A, what comes next?
B could be
0 or more Bs.
Yeah.
How would we represent the concept of 0 or more Bs defined from here?
for right language, it'd be something like BA or lambda.
You also have to end on an A,
Must be A.
so I did BA or A.
Could we put that A in the top though, since we can expand infinitely in the middle of this language?
That wouldn't be right terminal though.
Yeah. Yeah, so we need some way now to say, all right, we can create an arbitrary number of Bs. This says 1 or more Bs. How do we get 0 Bs?
Not an A.
Well, lambda would say we can basically terminate the grammar from here. We need this last A at the end.
Not term, we just terminate with A.
Yeah.
We have that in.
Yep. That becomes that, you could make this more complicated, add a second non-terminal here and then go further expand. But once we're ready to be done adding those Bs, we just select that last A, and that's the only way to end a sentence in this language. So it turns out that you can just parse this string linearly from left to right to produce a right linear grammar. Whenever you have a guaranteed symbol like this, that becomes and maps directly to the characters that you see before a non-terminal in that first definition. As soon as you see any amount of repetition or unknown, slap a non-terminal there. And then define that non-terminal in terms of that repetition or recursion and anything else that you know from that point. This process should be like reading this string from left to right.
For this to be fully correct, would you have to add a lambda because it's 0 or more, so it could just be AAA?
No, because the fact that we include within the non-terminal that it can be that A, we can immediately terminate.
You define this A in terms of that last A, and that generates the AA.
I also like to think about if you start from the tree, if you go S down to AA, then branch from that A down to either BA or.
Yeah, produce a B and leave room for more Bs, or terminate whenever you want. Yeah, so maybe if we wanted to draw this like a tree, we could start with our start non-terminal and then basically say, from here, we can, I guess just only one path we can go, so we go A. From here, we can branch the A from its two definitions. We can either end and terminate on AAA, or we can get AAB capital A. And then from here, we can branch and get AABA or AAB capital A. And from here we can branch, and you can see that this now starts to infinitely generate an arbitrary number of Bs at this position that represents this B star from here. Whenever you go right, you terminate and get a sentence in the language. Whenever you go left, you produce a non-terminal that adds at least one more B to where you were. So that's that process. So any constant characters, star closure, you use self-reference. Again, I just decided to use this as a B here because now we don't know what comes next. We can skip that step if we can see it coming and say B arrow A, but whenever we see, we just talked about this, A arrow B, we can just take this and replace the right-hand side of this with that B, and it makes the grammar simpler. Nothing about either of these is wrong. It's just about the simplicity of your grammar.
I don't like that our big A produces B's and our big B produces an A.
Yeah, when I first tried to write it, I did capital B, would be on the left-hand side, because that.
That's fair.
It's not incorrect either way,
Sub-zero.
because the capitals are always abstracts that represent some subset of
Yeah.
more characters.
There's certainly something to be said about logic that is correct, but is not easy to look at or not pleasant to look at. So you are welcome to use whatever symbols and characters you want. If you go away from what we've typically been using, it may be worth it to include that grammar quadruple that says something like, if the start non-terminal isn't apparent, you can then define what the start non-terminal is in that grammar quadruple. So this is basically the end of regular grammars. It's the simplest topic that we're gonna cover across the entire class, basically, is we need to know what it means to be left linear or right linear to show that we can produce them, but it's actually a fairly simple concept in practice. The actual algorithm that you apply to be able to produce a grammar from a regular expression is very simple, and regular grammars themselves have some pretty apparent rules to them as to why they are regular. It makes a lot of sense. If you have to linearly parse from left to right in one pass, you cannot store anything. You have no storage. So it makes sense to be able to parse the string from left to right, or the expression from left to right, or it's the exact same concept of linearly parsing some concept once with no storage. That is the beauty of regular languages.
We don't cover automata with storage in this class, do we?
Oh, we will.
But the tape one is the next one, right?
That is the second to next one. So the next topic I'm gonna start scaring you is probably, screen. It's probably the hardest topic we are going to cover in the entire class. There is a harder concept that builds off of this concept, but if you understand this concept, that concept will make more sense. So I think that this is the single biggest sticking point in this class. Now that I have your attention, let's dive into it a little bit. This is going to require, I'm going to be spending days on this, and I expect that after spending days on this, I will be talking to almost every single one of you in office hours at some point or another, possibly many times, and that is okay. This is not an easy topic to understand. That is also okay. We now have many tools that allow us to show that a language is regular. We can write a DFA. We can write an NFA. We could construct a regular grammar or find a regular expression. Those are the four ways now that we know how to prove that a language is regular. Any one of those will work. However, showing that a language is not regular is significantly harder. In fact, so significantly harder that it's as hard as everything we've done so far combined. It's probably going to take close to as much time as we've had for everything else to this point, because it's not straightforward initially. So we talked a little bit about the structure of a regular language. We know that it's parsable in one pass left to right with no storage. The information that we need as we are doing this is based on the state we are in and only the state we are in. We're not storing a history. We're not storing any data about where we've been or what we've seen. To do this, we're going to need to go back to discrete for just a second. Who remembers the pigeonhole principle? Show of hands. Little bit iffy. Let's refresh. We are trying to put n objects into k boxes, meaning that if there are more objects than there are boxes, we need to be able to have at least one box with more than one object in it. That makes sense, right? Let's say there are 20 seats in this classroom. There are more, but if there are 25 students in the class, at least one person is sitting on someone else's lap, regardless of legality. Just the idea of someone sitting on, it's gonna have to happen, or someone sitting on the floor. There aren't enough chairs for every student in the class. It doesn't tell us anything about whether there are empty chairs doesn't matter. We just know that there aren't enough chairs for every person in the class. If we wanted to figure out the maximum for this, we could take the ceiling of n over k, and that would tell us the minimum number of objects in some box. The minimum number of objects in at least one box. So now I have, I don't know, I have 4 drawers and I have 9 socks, not in pairs, individual socks. And I am so disorganized that I just throw my socks in random drawers. What is the minimum number of socks that must be in the drawer with the most socks in it?
4 drawers,
You have 4 drawers, 9 socks.
looks like 9 shoe slot.
So we put the first sock in the first drawer, the second sock in the second drawer, the third sock in the third drawer, the fourth sock in the fourth drawer, the fifth sock back in the first drawer. Now the first drawer has 2 socks in it. 6, 7, 8, 9, we would know the minimum number of socks in the drawer with the most socks in it is 3. There's no way to distribute that such that the drawer with the most socks in it had fewer than 3 socks in it. It could be that all 9 socks go in one drawer, that's fine, but then the drawer with the most socks has 9 in it. The lowest that number can be is 3. Some more examples. We like socks. Mathematicians really like colored socks for some reason. Who owns red and green and blue socks? You're my new favorite person. Mathematician, future mathematician.
Actually, I'm not wearing the red ones, but I do have my blue ones today.
Excellent. So we know that we have 3 pairs of socks, red, green, and blue. How many socks do we need to pull out of the dryer, assuming it's pitch black, to know that when we go from the laundry room back to our bedroom, we have a pair of socks? 4. You could, if you have 3, pull 1 of each color, and then you don't have a pair. That 4th sock must either be a pair to the first one, second one, or third one that you pulled out. Maybe the first 2 socks you pulled out have a pair, but if you're blindly going about this, you need 4 socks to know that you have a pair, knowing that you have 3 pairs of socks that are different colors. How many people do we need in a room to ensure at least 2 people have the same birth month?
Oh, the birthday.
Not quite yet. Actually, I don't think we need to go into it.
It's like that paradox thing.
It's the birthday problem.
It's a different related problem of how many people need to be in a room for there to be a more than 50% chance or more than a 90% chance that 2 share the same birthday.
Right, sorry.
What's it, like 366 people?
That would be to guarantee. What about to have a 50% chance? It's only 20 something.
Oh, is it like,
Because you asked how many do you need to insure it?
Ensure 2 people have the same birth month, not birthday.
yeah, sorry. Is this?
Okay, that'd be 13.
13,
Yeah.
yeah. Absolute worst case, the first 12 people all have a different birth month. So we need that 13th person to guarantee that 2 people share the same birth month. How about at least 5 people sharing the same birth month?
Well,
Lots of guesses, and I haven't heard the right answer yet.
Well, let's see here, it's like, 60. It's like you need everyone there to ensure, we need everyone there to ensure that least.
Still haven't heard the right answer. 49. Yes, it's 49. You have 48 people evenly distributed across the 12 months. That gives you 4 people with each month. That 49th person must share a birthday with some group of 4 that has a birthday. So that becomes the first group to have 5. 61 would be to have 6. So just kind of that basic refresher, we're going to use this concept in passing as part of this. So let's give you an example. This is a language that we covered early in this class. Remember our good old friend, a to the n, b to the n? Is it regular? If it is, then we'll be able to draw a DFA with a finite number of states. So think about this. Start to think about drawing out a DFA for A to the n, B to the n. Let's start this process. We have a starting state. We're going to call this Q0. We know that we need to, n is greater than or equal to 0, so Q0 should be a final state. This is A to the 0, B to the 0. From Q0, we read an A. Should that state be final?
No.
I'm going to draw these lowercase, they're easier to draw. If we see that A, what do we need to see next to be able to accept on the next character? A B. Drawing this like I'm asleep. That state is final because we've seen A to the 1, B to the 1. Great. If we saw an A, what would we have to do to get A squared, B squared, A to the 2, B to the 2? 2 A's, 2 B's. We need to see another A and another B. I'm drawing these as separate states. You could reasonably connect this B to that B since it accepts already.
Well, you need 2 B's though.
Yeah, no, we don't. Yeah, we need 2 B's. You're absolutely right. Put the second one. Yeah, second one we could connect to that and make it simpler. So from here, we could see a third A, and now we need 3 connections of B's. So we have Q6, Q7, Q8, Q9. And these are all B's. Everything else from this would go to a trap state other than being exactly that, this final. Is this process ever going to terminate?
No.
No, this is just going to continue, and each one of these are going to get longer and longer and longer in a diagonal. So this really simple language needs some storage to be able to see. Once we see our first B, we need to know how many A's we've seen to be able to pair B's to A's that we've already seen. That concept would allow us to recognize this language, but we do not have that structure within the rules of a DFA. So we start to see this happen when we start to construct a DFA for it. But if we actually wanted to prove that no DFA could exist for this, you would be relying on an intuitive argument saying that this goes on forever. There are some languages where that intuition is much harder to build than A to the n, B to the n. So it's very useful to have some kind of algorithm to actually, some process to go through to actually prove that a language is not regular. So no finite DFA exists for A to the n, B to the n. We will come back to A to the n, B to the n a lot as we talk about this, because it's basically the simplest example that we can find.
If you prove by inductive, prove that it is infinite.
Where it's actually going to be fairly similar to what we end up doing. We're going to use proof by contradiction, but you could easily make part of that proof by contradiction an inductive proof. So we're going to use the pigeonhole principle here momentarily to say, well, if there are an infinite number of possibilities for n, and there's a finite number of states in the DFA, then we have to say, well, there are multiple abilities to map A to the n to a particular state. Does that concept make sense? We're going to, for a second, assume A to the n, B to the n is regular. If it were regular, then there'd be a DFA with a finite number of states. Since A to the n is greater than or equal to 0, there are an infinite number of natural numbers, including 0, which is totally a natural number. Don't even get me started. But there are an infinite number of accepting states for that. We need A to the 0, B to the 0, A to the 1, B to the 1, A to the 2, B to the 2. There are an infinite number of those. If this DFA were finite, then we would need to be able to map multiple instances of this problem to a single accepting state or to a single path through this DFA. We can do that with the pigeonhole principle. So from here, we just proceed with a proof by contradiction. We start this process by saying, assume there exists a DFA that accepts a to the n, b to the n for some value of m. We can then state that there is a state such that when we transition from Q0 reading a to the n and transition from Q0 reading a to the m, we get to the same state. Does that make sense? Think of it like this. We have our Q0 on an A, Q1 on an A, Q2 on an A, Q3 on an A. So this is our first A, second A, third A, fourth A. We're not even starting to consider B's yet. This is a finite DFA, and this n can go from 0 to an arbitrarily large number. In order for this to be possible at a finite number of states, we have to have at least 2 different values of the number of A's that lead to the same state. Because otherwise, this just continues forever. And we receive an infinite number of states. So if this were to be regular, this would have to stop somewhere. Since that is infinite, and this is not, we need at least 2 values of A that map to the same state, that reach the same state after parsing some different number of A's. It very quickly becomes apparent that that's not possible. But it becomes the basis of our proof. We know that this DFA that exists because a to the n, b to the n is totally regular, trust me. Then we need to be able to, when we get to that point, have a transition from this point to a final state consuming some number of b's. We know we can get to this middle state Q by consuming m a's, and we can get to the final state with this that allows us to be able to produce a to the m, b to the n. If that makes sense. So there was a way basically to get from the starting state via some transition to this middle state. So this is going to be Q0, and this is going to be this concept Q, this middle state where we can get there via consuming either m or n A's. Which was needed because this is a finite state machine. There are a finite number of states. I'm just taking this assumption that this language is regular and running with it and seeing what kind of garbage logic I can come up with. If I do this from Q, then there also needs to be a way to get to a final state that we're going to call Q sub f via reading some number of b's. And let's say we can get there because we know this language accepts a to the n, b to the n. We say that we can get there consuming n b's. So we know that this path must exist. This allows us to say, if we consume m a's getting to Q and then n b's getting to the final state, that this accepts the string a to the m, b to the n, where m and n are different values. This is not in the language. So any finite DFA that could do this would need to be able to accept this, which is not in the language. That creates your contradiction. Question?
So we're just proving like a false positive.
Yeah, you're running with this assumption, and then you are generating garbage, showing that this cannot possibly be. You're generating that contradiction. If this DFA exists, then it must accept this string that is not in the language. We'll come up with a better process for this that works in more general tomorrow, but I'll answer questions about this for now.
How do we know that there's not another DFA that would work?
we will actually show that. We'll be able to show that given that we have the minimal DFA, that we can do that. And we will also show in general, basically, that any DFA that represents an infinite language, I'll actually get into this in a lot more detail, but basically you start at a starting state, you reach some middle state. That state via some number of other states is going to be able to loop on itself, thus creating the infinite language. And then you go from this middle state to a final state.
So we're
So-
simplifying it and Q, the middle state, could be a combination of many states.
Yeah, so, yeah, we can do this loop an arbitrary number of times. So this needs to be in the language, this followed by a single loop here, plus that needs to be in the language, this followed by that and that needs to be in the language, etc. And we will show, the general way to show this is that any DFA that accepts strings longer than its number of states that are in it must have this particular form, and this particular form breaks for every single regular language. Or for every non-regular language. We assume that it's regular, we try to fit it in this form, we can start generating strings that aren't in the language via this process. And as soon as we generate a single string that's not in the language via this idea, we can terminate and say, assuming this was regular, this needs to be in the language. Since it's not in the language, no such DFA can exist, because you're working with an abstract DFA rather than actually drawing out a real DFA. So it gets really abstract. You're going to start working with the idea of a DFA instead of actually being able to draw it out, which is really tough. But once it clicks, it's really powerful. So we will focus and continue this process tomorrow and probably a chunk of next week too.
I hope we spend confident speak on this.
It's tough. There's a lot here. I have office hours starting now, if anyone has any questions.
I got a question on Zoom, if the lemon stuff is gonna be on the,
Oh, yeah, no, this is the cutoff. After regular grammars, we are done for the first exam. This is the first thing that will be on the second exam.
thank you.
Yeah.
Second, it's already.